Hello everyone. So in continuation with the friction numericals, in the last few sessions you have studied about the various types of friction numericals related to block friction, and when there are strings present, how do we consider? So just with a little bit of brushing up of the previous, we know what is friction. How will I show a friction force? Looking into this particular diagram, if we have a force P which is going towards the right side, then the friction force is always developed opposite to the applied force P. Now consider this a block which is placed on an inclined plane. If P is the applied force which is on top direction, then the friction F is always going to be developed to the opposite to the applied force. Right? These two blocks show the same thing. We have seen numericals of such kinds where two blocks which are connected with the help of a string and a pulley arrangement. So to this particular arrangement, if a force P is applied in this direction downward, so what happens? Because of this force P, this block is going to move down, and this string arrangement is going to pull this block on top because of the applied force. So hence friction, the block moves down, so friction is up. This block moves up, so the friction force F is downward direction. Now there's one more example here, very important one. We know that in case of strings, we always consider the reactive forces to be tensile in nature, that is two arrows inwards. If we have any other bodies like two blocks coming in contact or a rod, it is compression forces or compression reactive forces, right opposite to the sign convention to this. Like tension, we show two arrows inwards. Compression, I will show two arrows outward. So this is an arrangement where there are two blocks connected with the help of a rod, and one of the block is on an inclined plane and one block is resting on a horizontal plane as shown, and this is a rod, metallic rod probably. So the here the behavior of the rod is completely different from the behavior of a string. Now rod is a compressive member where I said reactive forces. So when this block is going to move down, what happens is this block is going to move towards the right side. You can just make this arrangement or analyze or visualize. You'll understand when this block moves here, this block is moving towards the left. And if I'm pushing this block on the top, this block is going to move to the right. So based on that, I have shown the two friction forces. Considering first the block is moving on top, so friction is down, and this block moving on top is going to pull this block towards the right, so the friction developed is towards the left. First case. Second case, if the block is moving down, the friction force is upwards. As this block is going to move down, this block will move towards the left, so the friction is shown towards the right. This is a bit confusing concept. For now, I hope you have understood. If not, we will be again explaining this when once the college reopens. Then we have seen probably this kind of numericals where a block over a block attached with a string. So string will have tension and this force P is applied. This force P tries to move this block towards the right side. So the friction developed between this surface and the surface is towards the left. Balancing this, because this block tries to stay, upper block is trying to stay in constant way, I'll have opposite to this friction here developed. These two are F1, this will be F2. The same one when there is an inclined plane. So these particular sets of example you have gone through in the last week. I hope you all have understood the numericals and tried to solve them also. I will be taking up today the ladder friction. So there are two cases basically in ladder. All of you are aware of a ladder placed against a wall and a floor, and you must have tried climbing also. What happens when you climb on a ladder? Say, consider there is a ladder placed like this, arrangement shown, and weight is your weight, you are standing on the ladder. This ladder tries to slip downwards, that is, it is going to simply move like this downwards. So at this junction, the movement is going to be at the downward side, and this junction the ladder is going to move the left side. So considering that, I have to show friction right opposite to the movement of the object. So now when I'm saying because of the weight, the ladder slips, this part of the ladder, when it comes down, the friction force is going to be shown upwards. Similarly, at this junction, when the ladder slips, this point of the ladder moves towards the left. So the friction developed will be towards the right. Okay, this is one condition where the ladder is slipping down. The other condition in case of a ladder is because it should not slip, I will apply a force P in this direction. So what happens when I apply a force P in this direction? This ladder will try to move in opposite direction. So this junction moves up and this junction moves towards the right. So when this junction is moving towards upwards, the friction developed is towards the bottom side. And when this junction is moving towards the right, friction developed is towards the left side. So this is the concept that we are going to use in friction numericals. We'll have to put the free body diagram for the friction force F, and you have normal reaction N acting perpendicular to the plane, as we all know. Okay, so let us take up the first example. A ladder weighing 200 Newton. This is the weight of the ladder. So weight always acts at the center. So irrespective of whether they have given you a figure or not, I will always show the weight of the ladder at the center of the ladder. Okay. So a ladder weighing 200 Newton is to be kept in position as shown in the figure, resting on a smooth floor and leaning against a smooth wall. Determine the horizontal force required to prevent it from slipping. I don't want the ladder to slip. So what is that horizontal force P applied so that this will not slip? When a man of weight 700 is at a height of 2 meters above the floor level. So there is a man whose weight is 700 newtons at 2 meters above the floor level. They've given you the diagram. This is the wall and the floor arrangement. It is smooth. So whenever you come across this term smooth, it indicates that I will ignore friction F. If you come across a smooth surface in any numerical, it indicates I will not account for F. Smoothness tells us that there is no friction present. Apart from F, I will be incorporating for the normal reactions that are coming on the structure or on the body. So this is the ladder. The weight of the ladder 200 Newton exactly placed at the center. Now while giving, he has given us the height, vertical height, so which is 3 meters. So I have to place the weight exactly at half, meaning 3 divided by 2 at 1.5 meters height. I will first place the weight. Then he says there is a man 700 Newton standing at 2 meters above the floor. So from here 2 meters above the floor, I have 700 Newton man standing like this. The ladder makes an angle 60 degree with the horizontal. Determine this force P which is applied, or what is the value of this force P so that the ladder is not going to slip is the condition. Let us now look into the free body diagram. So the ladder 60 degree, NA/NB, I've written RA/RB, you can also call it as NA/NB. This RA/RB, that is your normal reactions, and this force P, I have to know. I have not shown for F because the surfaces are smooth. For the same example, if he doesn't mention that the surface is smooth, I have to account for the force F. So F is not shown over here, and the given external forces 200 and 700 are shown on the figure. We have to find the value of P. And this comes under equilibrium of bodies. So we will be applying the equations of equilibrium. Now, coming to equations of equilibrium, this is a non-force system because we have forces which are acting at all the places. Like for example, point A there are 2, point B there is 1, and there are 700 and 200 at different points. So this belongs to a non-concurrent force system. Ladder numericals fall under non-concurrent force system. So what are the equations used in case of non-concurrent force system equations of equilibrium? We will have 3. That is summation f of x equal to 0, summation f of y equal to 0, and summation m, that is moment of all the forces about any one point is equal to 0. So now to solve the latter examples, keep in mind I have to make use of 3 equations of equilibrium, fx equal to 0, summation fy equal to 0, and summation m equal to 0. Then only I will be able to get the unknown reactions or unknown forces. Okay. So solution, as the surface is smooth, hence no friction is accounted. I have not shown any F in the free body diagram. Are non-concurrent in nature, so we use fx equal to 0, fy and m equal to 0. Okay, so let us apply summation f of y first. F of y means all the vertical forces. Vertical is 1, 2 and 3. So Ra is positive upwards and these two are negative. So I'll write Ra minus 200 minus 700 equal to 0, wherein only Ra is unknown. I get the value of Ra, reaction at A. Then summation f of x equal to 0. X is horizontal force. One is this, another is this. So plus b minus b, Rb is 0. Both of the values are not known, so I will call it as equation 1. Now I have to apply the third condition of equilibrium, that is summation m equal to 0. Let us consider the moment. Where to consider the moment? Either at point A or at point B. If I take the moment at point A, I will get the value of Rb, but I'll not get the value of P. I can substitute in equation 1 and get the value of P. If the moment at B, I can find the direct value of the force applied P and then substitute and get the value for RB. Anyone. In this particular case, I have taken moment at point B because first I want to find the P value. Before that, if I'm taking moment at B, just look into this figure. When I'm taking moments, P into perpendicular distance and anti-clockwise, R into perpendicular distance clockwise. RB is passing through B, so it is 0. 700 into perpendicular distance, this distance, and 200 into perpendicular distance, that is this distance. So I have to first find all those distances. So there is a figure over here. This is point A, point B. It is not very neatly drawn, so sorry for that, students. So but still you can make out what I have written. This is B. You have 200 and 700 forces acting here. This is your force P, this is Ra, this is Rb. Now this 200, which is at height 1.5, if I drop perpendicular from that point, I call this particular distance as x1. I drop a perpendicular from 700 newtons to the horizontal and I call that particular distance to be x2. I know this height is 2 meters. And similarly, in the entire big triangle, this is given as 3. So the entire triangle base is x3. Okay. So I have to find the values of this x1, x2, x3 so that while taking moment, I will be multiplying them by the distances. So we should find the horizontal distances x1, x2, x3 from the given triangle. Now what we'll do, we'll take this smaller triangle first. In this triangle, I know this height is 1.5. This base is x1. I know this angle is 60. I will apply tan of 60. Tan 60 is opposite by adjacent, 1.5 by 1. So I get the value of x 1.866. Second, the next set of triangle, that is this bigger middle triangle. So tan of 60 is opposite, that is 2 meters, by adjacent, that is x2. 2 by x2, I get the value of x2. Similarly, bigger last big triangle, tan of 3 by x3. So I get the value of x3 is 1.732. We found all the three values of x1, x2, x3. I know the vertical heights 1.5, 2 and 3 meters. Now let us take moment at B. So I'll just zoom in so that you can see the diagram and the equation also. Coming to this force, Ra into perpendicular distance is what? It is total distance is x3. So Ra goes to B in a clockwise direction. So Ra into x3, Ra goes like this. Ra into x3. Mine P into perpendicular distance is 3. It goes in anti-clockwise direction. So minus P into this distance is 3. Then 200 into this is the perpendicular distance. What is this distance? It is x3 minus x1 will give me the remaining distance. So minus 200 into x3 minus x1 and 700 into this perpendicular distance, and that is what x3 minus x2. x3 minus x2 will give me that distance, right? RB is passing through it, so it will not give me any moment. So the moments that I'm going to take is because of P, because of Ra, 200 and 700. That's it, no other forces. Okay, substitute. Ra into x3 minus p into 3 minus 200 into x3 minus x1 minus 700 into x3 minus x2. On substituting, because we have all their values, I will directly get the value of p, that is 327, and I will substitute p in this equation. So p is basically equal to rb, so rp value is 327. So this is one type of example on ladder friction, where I will be finding the force applied at the base of the ladder to avoid it from slipping. There are three types of numericals in ladder friction. This is one. We have another. I'll be taking it next. That is finding the angle here, theta. And then we have another type of numerical also, which will be done. Hope you have understood this. If you have any queries, please revert back. Contact any one of us. We'll be there to solve your queries. Thank you.